As part of my series on the Onium theory, I wanted to talk about the Eta and Eta prime mesons. They're important because they have the same nonsensical type of formula that's used in several different mesons within the quark model. So it's important to review that they can be treated much more easily and simply with Onium theory. To begin with, the Eta has a mass of about 548 MeV per c squared, while the Eta prime has a mass of approximately 958 MeV per c squared. It's a difference of about 410 MeV per c squared, so not a lot, and they appear to be related, and that's because of their decay products. The Eta predominantly decays either to 3 neutral pions or 2 charged pions and a neutral pion. The Eta prime, on the other hand, tends to decay to an Eta and 2 pions, either 2 neutral pions or 2 oppositely charged pions. And so the Eta prime appears to be an Eta with 2 extra pions added to it. And in Onium theory, that's what we say it is. We actually follow the scientific evidence, unlike in the quark model. And so we have 3 pions in the Eta, 5 in the Eta prime. Now we can do a quick calculation of the mass using Onium theory. In Onium theory, we recognize the quantization of mass of mesons and baryons at 70 MeV per c squared and 35 MeV per c squared. And as I mentioned with kaons earlier, kaons can be composed of, in a previous video, the kaons are composed of 2 pions, and each pion contains 3 particles, and each particle contributes 35 MeV per c squared to the relativistic mass energy, for a total of 210 MeV per c squared. So to get an idea of what the Eta is made of, we can sum up the mass of a neutral pion, 2 oppositely charged muons, and 210, and we get about 10 MeV per c squared more. And it's interesting here that we have to use muons rather than pions, which indicates that rather than counter-rotating and magnetically coupling, that the 2 muons are rotating in the same direction, which is how they're able to retain the lower mass energy like muons normally have. So that means the structure is a little bit different from the kaon, and that's why it has mass energy a little bit more than the kaon, but has 3 pions in it rather than 2. The Eta is the only meson I've identified so far with only 3 pions. And then similarly, so we can have a model here where a pion is orbited by 2 muons. And then similarly, we can estimate the mass of the Eta prime by taking the mass of the Eta plus 2 muons plus 210. And once again, it's about 10 MeV more, which indicates that they're orbiting all in the same direction so that they have the reduced mass energy. And the Eta prime model looks like an Eta orbited by 2 oppositely charged muons. The Onium model is very simple, straightforward. It sticks to the evidence presented to us by the decay products, and it gives us mass energy based on relativistic mass. In the quark model, on the other hand, we have these nonsensical formulas that I've talked about in other videos. In the Eta case, it's an up and anti-up minus a down and anti-down minus 2 strange and anti-strange quarks divided by the square root of 6. And if that doesn't sound like totally numerological nonsense, then what can I say? So basically, the up and anti-up annihilate, the down and anti-down annihilate, the strange and anti-strange annihilate. So this is nothing divided by the square root of 6. Now, to be fair, at least within their model, they consider the phi meson to be a strange and anti-strange meson, although they also think it's a superposition of these two formulas. So if you add 1,020 MeV, or actually subtract 2,000 plus MeV particles from this, you could try to get a negative mass energy for the Eta particles. So deriving the mass that way doesn't make any sense. Dividing elementary particles by the square root of 6 doesn't make sense. Subtracting elementary particles from each other doesn't make sense. Up Onium and down Onium don't exist, so having them in some sort of metastable state doesn't make sense. So this whole thing, while I understand the basic theory of coming up with this interactive wave model, but it's nonsense. Especially when you can do a very simple orbital model like this and explain it. Now the equation for the Eta prime is slightly different, but equally stupid. You have the up and anti-up, the D and anti-D, plus a strange and anti-strange, and divided by the square root of 3 this time. So we have a case where everything about this is wrong if you're trying to do a physical interpretation of what the equation would mean in any sort of real-world sense. So we have the same situation where if we try to do a physical real-world interpretation of this equation, it's total nonsense no matter how we look at it. And so the bottom line is quark theory is unnecessary, and it's an unnecessary complication. It should be discarded. It shouldn't even be used when you're dealing with Eta and Eta primes, or any other mesons for that matter, or baryons. But I'll get into other mesons and baryons in future videos. Well, I hope you enjoyed this short but sweet video and learned a little bit more about the Eta and Eta prime mesons, and a little bit more about quark theory and onium theory. And if you like my video, please like, share, or subscribe. And if you want to learn more about onium theory, I have a book, Goodbye Quarks, the Onium Theory, that explains all these particles in a lot more detail and explains how the theory works. And then if you're interested in my quantum field theory, I have 2 books on quantum field theory that are available for sale, and the links are below. And I will add some links for some papers on onium theory as well, so you can reference that. So thanks for watching.